the student chapter meeting, the first of this kind in this year. We're meeting after a long time, and it's particularly heartening to see a reasonable amount of turnover today to see these people over here. I particularly welcome Professor Ramanujam, who is here to give the talk today. Before we go to the talk, I thought I will just say a few words on the student chapter, what is its role and why we are here. Okay, so the computing activity has been in the institute or has started way back in the 60s, starting with people working in image processing, speech processing, and related things, and subsequently activities in the computer science department started about 50 years ago. Now computing is in the ECE department, EE department, as well as in the ESC department, so as well as in other places as well. So computing is all over. And if you look at the current state, what we lack is that there is no organized way of doing these things, right? Activities are managed ad hoc. There is a limited career guidance which is given to students, and the community is fragmented and there are no interaction among them, right? So the chapter essentially facilitates some of these activities in an organized way. It acts as a platform for information and it offers opportunities. This is essentially why we have the IAC student chapter of the ACM, and I welcome all the students to become a part of it and get benefited by that. That's the reason for this. In the previous year, the chapter started, I think, in 2019, and we had an inaugural event on the 13th of June, 2019, and a talk was given by Dr. Gargi Dasgupta, Director of IBM Research. We also had talks from Dr. Manish Gupta and Dr. Milind Tambe from Google about the Google research activities. The chapter also helped in organizing a winter school. ACM India has been organizing a series of summer and winter schools, many of which, all of them are really very useful for the students, particularly students from outside. Students from IAC, of course, they also participate in this. IAC faculty conduct many of these events. And the one that was conducted in January 2020 was organized in the CDS department, and the student chapter of IAC took active part in that, in doing a lot of voluntary work in that. Okay, now what have we planned for this year? We have planned for many more invited talks on topics which are closely related to what the students would like to hear. We also plan to have panel discussions which talk about entrepreneurship, career advisors, career choices for graduate students, and so on. We also want to have a skill-based workshop about ongoing research and technology, and many more such events. And if you have any specific suggestions, please feel free to talk to the ACM volunteers who would be able to take this forward. Right. Apart from this, we would also like to request the students to actively participate in the ACM India student chapter. Currently, we have 4 core committee members and 25 student members, but we really need to grow this community to a large extent. And we need more people for office bearers, we need more people for volunteers, and of course, website management and so on, right? So if you are an ISC student and an ACM member, please join this group and actively participate in this. This is the website that is created for the IAC student chapter, and it contains the details about membership, the events that are being conducted, and the positions that are available, mostly voluntary positions that are available. So if you would like to become a member, please feel free to do so. The information is available there, and the volunteers are here. They will also be happy to talk to you about it. I think with those few words, I once again welcome all of you and request Professor Deepak D'Souza to introduce the speaker of the day. Deepak.
Thank you, Govind. So it's my pleasure to welcome all of you all to this talk today by Professor Ramanujam. So Ramanujam is a well-known computer scientist, especially in the theoretical computer science community in India and abroad. And just to give you a bit about his background, he graduated from BITS Pilani and then joined up for a PhD at Tata Institute of Fundamental Research in Mumbai, and then spent some time in the City University of New York after that, and then finally came back to India and joined the Institute of Mathematical Sciences in Chennai, where he has been for the last couple of decades, I think. And so Ramanujam is well known for his work in logic and automata. And he has made several contributions, not only in these areas, but in application areas like security and games and theory of distributed systems. He's also very active in education for science education in the country for school children. And particularly in Tamil Nadu, he has, I think he has started this Tamil Nadu Science Forum, and he edits a monthly magazine for school children on science. And he's also participated widely in many, curriculum-related committees, both at the Tamil Nadu state level as well as the national level, including NCRT and the National Curriculum Committee. And of course, he's a very engaging and motivating speaker, I should say that. So you all should look forward to a good talk. Let me just add that when I was a master's student back in Pune, so Ramanujam had come down. I don't know how he had happened to be in Pune at that time, but he came to our university and he gave a talk. And all of us had, were very excited to have someone like him come and speak to us, because he's talked about some distributed algorithms which probably went over our head at that time. But the way he put it in terms of, Byzantine generals and, attacking at dawn and sending messages which could be intercepted. And it was interesting, and that kind of motivated us to find out more about math science and CMI. And I ended up doing a PhD at CMI and math science. So welcome, Jam. It's a pleasure to have you here. And over to you. So if you use a mic, okay.
So can you hear me? Is the mic on? Yeah. Okay. So yeah, good afternoon, and thank you for those kind words of introduction. Yeah, so this talk is not for those who know logic, and this is, as I said, I told Deepak to introduce me and then walk out, but yeah, he chooses to stay. And in fact, he just said a moment ago that these are student-initiated talks, and the person to blame for this talk is sitting there. I mean, Sheshadri was the one who picked this topic and picked me to give this talk. So yeah, so okay. Actually, I should have mentioned something that maybe about 20 years ago, 21 years ago, I came to CSA to give a course of lectures on logic at the invitation of Professor Preeti Shankar. And I think Deepak joined within a couple of years after that. And then she said, we'll have logic courses here. But there was no mathematical logic course. And Kamal Lodaya and I came and gave a course of lectures on logic somewhere in the older set of rooms. And so I'm used to lecturing on logic in IISc, I think. Even before that, when I was a graduate student in TIFR, I came and gave some lectures on logic here, I remember. So it goes way back. And a moment of pleasure for me was last month, Vigyan Prasar had announced that they were putting together a book on, so this is Azadi Ka Amrita Mahotsav, all sorts of 75 something is happening in the country. So they were putting together a book on 75 Indian women scientists. And I was asked to contribute, and it was my pleasure to write a biography of Preeti Shankar in the volume. So just to mention that on this. Okay, so thanks very much. And so let me begin with, so thanking you all for the invitation, and especially Sheshadri for pursuing this and pampering me really for coming here. So here's a quote, and this is from George Boole on the laws of thought. Right? I mean, look at the grand title, the laws of thought, nothing less. And he says that it is to investigate the fundamental laws of those operations of the mind by which reasoning is performed, to give expression to them in the symbolic language of a calculus, and upon this foundation, to establish the science of logic and constructivist method. I mean, very, very grand aim. Okay, so we'll have more to say on Mr. Boole. So here is a puzzle. Okay, here's a puzzle to motivate things. And so many of you may have heard of this puzzle. It's a very famous puzzle, popularized by Martin Gardner, who wrote this series of puzzles in Scientific American. So I picked two integers, two positive integers, distinct ones, and between 1 and 100. And let's say that the sum is less than 100. So these are small numbers that we are talking about. And there are two people, Miss Product and Mr. Sum. And I go and tell Miss Product the product of X and Y. And I go and tell Mr. Sum the sum of X and Y, right? And then the following conversation happens between them. Miss Product says, I don't know what X and Y are. Mr. Sum says, I knew that you didn't. And Miss Product says, now I know X and Y. And then Mr. Sum says, so do I. Find X and Y. Obviously, that's the puzzle. Now, look at this communication here. Nobody is saying anything about the numbers. Or are they? I mean, right? So there is communication going on. And at the end of which, this is something I do with school kids, class 8, class 9 kids, and they actually find X and Y, right? So clearly we are able to infer something about the numbers and without actually saying anything about the numbers. It's only a statement about knowledge and ignorance, right? And well, what is the information content of the first statement? I do not know what X and Y are. What is the information content? Anybody? Sorry? No, that's what she's saying. Clearly, of course, there is a superficial information, but from that, can you infer anything more? Well, I've already told you that X and Y are distinct. They're not prime. You can't both of them cannot be prime, right? If both were prime, right? If, for instance, I had told her the product 35, she would have immediately said 5 and 7, right? So it can't be so at least one of them is composite. That is the information we get. The second one is deadly. Okay, now the information content of the second one, because he knows the value of X plus Y, right? From that, he is able to figure out that one of them is composite. That's what it means, right? From the information contained in, so basically, then Mr. Sum has to think about different ways of summing that number and see that at least one of them has a composite number, right? Now, what does that mean? Oh, no, that we're not going to do this. It will take some time. I mean, okay, you need some paper and pen and you have to sit and do something. And then comes the third statement. From that information, she's able to figure out, now I know X and Y. What is the content of the last statement? So do I. It says that X and this combination is unique. Because if there were two different pairs that would work for the previous 3, then he couldn't figure out, right? So the last one says, now I challenge you to write a statement that actually compresses all this information in one single sentence, right? The last one, in fact, so you are saying there exists X and Y and a unique pair at that, which satisfies certain conditions, right? And I assure you that you can actually write it as a statement in first order logic and arithmetic. First order arithmetic is good enough for saying this, and you can actually write that. But that doesn't mean that saying that there exists, a unique pair XY such that all this happens, doesn't mean you can find it. That's the relationship between logic and computation. But very often, if you can write such a statement, I assure you that you are well on the way to computing the X and Y as well. So in some sense, what I want to talk about, this is maybe like a one-slide summary. right? So when I say logic, I'm not talking about particular logical language, messing with it, and loop invariants and so on. So all that is, of course, important. But it's about inference. It's about something very interesting like this. That, I mean, Deepak already mentioned that I've been working in security theory, right? One of the big things in security is this eavesdropper watching communication channels and trying to figure out kya ho raha hai, right? I mean, encryption is not about using RSA or this thing. Huh? Encryption is basically hiding something from anybody else who's listening, right? That's about all there is. But this is not about information hiding. This is about information revealing, right? So it's perfectly all right to ask what is the information content of a communication, right? But that is a logical matter. It's a matter of inference. And once you get used to thinking in these terms, there's a lot available for you to think about. And like I said, this connection between logic and computation is also very important. So the question that this thing started with was, why should we study logic, right? I mean, logic is, especially for, and there is a second one, if you're a computer science student, okay, logic is all great, but why the hell should I study it, right? I mean, then if we can somehow try, I mean, the point is these are, I mean, I have another lecture called Why Should We Study Theory of Computation? So, and, you know, and this is a very, I mean, I don't know how often, I mean, have you had Theory of Computation as a compulsory course? Anybody? You have, right? Has anybody gone to maybe Deepak or anyone asking why is it a compulsory course? Right? But I think we should, right? It seems reasonable to ask, why should I study algorithms? I mean, I also have another lecture called Why Should We Study Algorithm and Why Should We Study Algorithm? I mean, if I'm going to be a hacker, I'm going to be, you know, developing web pages, I don't know what all. Why the hell should you hassle me with all this stuff with graph algorithms and numerical algorithms, God knows what else, right? But I think these are reasonable questions, and I think there are reasonable answers. I mean, as he said, I'm a theoretical computer scientist, unabashedly and unashamedly so. And let me make it very clear that I think computer science students should study algorithms, learn theory of computation, learn some logic. But why? And this lectures came as a kind of thing, because invariably when I go to colleges and so on, people know, nobody ever goes to, I mean, in fact, it started with my being in some board of studies somewhere, and I was invited for a talk. And then I was telling the students that, you know, I came for this board of studies meeting. And then it occurred to me, do you know what board of studies does? And then I found that students had no idea. And I said, look, board of studies is supposed to be deciding the curriculum. So here I'm standing, so you should ask why is this there and why is this not there, etc. So it started off with that. But anyway, so, and I think this is also a very reasonable question to demand an answer to, right? If I suffer through a semester course in logic, right? I'm a computer science student, you're making me sit through a semester course. What can I expect to learn? Of course, you know, this kind of thing can only be said for somebody who's reasonably sincere. I mean, if you walk through the thing, you may not expect. But so what are the kind of things that, you know, there are these fashionable terms like learning outcomes and so on, right? I mean, I don't know about that, but what can we expect? So I hope some vague answers can be provided at least. And that's what this discussion is about. So there is this very famous paper by Eugene Wigner, who talked about the unreasonable effectiveness of mathematics in the natural sciences. And you know, he says a physical theory's mathematical structure often points the way to further advance in their theory and even to empirical predictions. I mean, the famous example is the Dirac delta function. And Dirac was very clear that he wrote the delta function because, you know, it's elegant. He said nature cannot be in any other way. And this is bizarre. Huh? Why should nature follow simply because the Dirac delta function looks very neat? But you know, quantum electrodynamics is one of the most verified ones. But so Eugene Wigner was posing this question: why should it be so? And I would say that I mean, everybody says that logic similarly pointed the way towards computer science. And well, there is a paper by Moshe Vardi and Joe Halpern and several others mimicking this, calling it, the paper is titled Reasonable Effectiveness of Logic in Computer Science. And some of the things that I'm saying is of that kind. Now, something happened. Okay. So now there are many areas of computing which are logic driven. As of now, I don't see things like machine learning or not. Just to, one should always say non-examples as well. Otherwise, if it applies to everything, it's trivial. So, right? Now, most spectacular in recent times is database theory and hardware systems design and verification. Software verification also, there is a lot, but it's not anywhere as dramatic as it has been in the case of hardware design. And perhaps the deepest impact is in complexity theory. But then if you don't care for complexity theory, you may not care for that. But then there has been major impact in areas like programming language theory, artificial intelligence, where you see a lot happening now, concurrency theory, distributed algorithms, so many areas of this kind. Now, again, just because something has wide applications, that is not sufficient reason to conclude that therefore I must study it. I'm just saying that, okay, some reason that maybe it's very likely that you're going to get into one of these areas, so it's a good idea to learn some logic. That's one possible answer. Potential impact, I would say, I mean, not exactly the kind of dramatic impact that I mentioned, but you can see potential impact in the kind of areas that I have been studying, namely security theory, game theory, and so on, where you can see, room for logic. Now, but the connection between logic and computation goes really way back. And the history of computation is really tied to logic. And the oldest that I would like to refer to is Leibniz, and where he talked about a machine to derive logical relationships. And Leibniz has this beautiful quote where he says that, I can see in the future there will be a time when two people who are arguing at some point will say, okay, let's stop talking, let's calculate, right? So the arguments should be actually done by machines. That's what he wanted. Calculemus is what is a grand dream. He would be very happy with today's theorem provers, and machine checkers and so on. Boole, of course, and in the mathematical analysis of logic, that is a very famous one. And we just had the Boole bicentenary where we had a lot of interesting discussions on these things. There is also Jevons who talked about logic machines. He built a logic machine as well. And Peirce talking about calculating. In fact, he actually said this in so many words. Calculating machines are specialized logical machines. And, Peirce wanted to go further, ahead of his time, so he couldn't do much. Now, there's also a deep link to mathematics. And if you ask what makes mathematics so reliable, well, it's based on proof. Science is based on experimentation, mathematics is based on proofs, and that's what you would call the high road to truth, right? Now, the question is, but then what is a proof? What is a rigorous proof, right? Is a proof something that convinces a skeptical adversary? Makes sense, but that is a sociological thing, right? Is a proof something, a sequence of statements where you have a deduction system and you're going from axioms, but nobody writes proofs like that, except in high school geometry or in some, So what is a rigorous proof? How do you even define what a proof is? And that's a serious problem, right? If you say mathematics comes from the fact that it's based on proof, but then most of the proofs you write are things like clearly and evidently and so on, and obviously and so on. And there's nothing, and you read it and it's clear as mud, right? There's nothing clear at all, right? So mathematicians were bothered by this, and people were bothered by it, and it took a very long time before people could actually. I think more or less now it's clear after Church, Gödel, Kleene, Post, Turing, and so on, that if you're going to talk about a rigorous proof, it better be something machine checkable. Now, of course, which machine, right? Well, so basically, it comes down to something like computable. Right? So this is more or less what you might call an acceptance that has come in the 20th century over a long course of mathematical philosophical investigation. Right? And so that connection is, so if you really want to know what finally that you would accept, and one of the most convincing things that we saw recently was the proof of the Kepler conjecture by Thomas Hales about 10 years ago, last decade, certainly. And 2015, that proof was completely machine checked. And this is one of the high points for people doing theorem proving also, that they could do. And so this is probably going to become the norm, that there are controversial proofs which are based on some computation, some of these things. Machine checkability as a standard of rigorous proof, many mathematicians are coming to. And so computation lies at the heart of mathematics. And that's not very new, but it's something to note. But how does it actually get there is where logic plays an important role. Now, are there laws of thought? If there are any, do they permit calculating those results, right, as Leibniz wanted? And that was really the question that drove this remarkable mathematician in 1854, and that is George Boole. And Boole, an interesting person. I mean, he got to all this, I think, after the age of 40. So for those who think about Fields Medal and all that, it should, right? So, and he was basically working on differential equations and these. And he took time off to write a couple of books, and one of them was this. There are these two books, and where one is called Mathematical Analysis of Logic, and then the second one, which is really the grand title, An Investigation of the Laws of Thought on which are founded the mathematical theories of logic and probabilities, 1854. Now, what an audacious idea, right? To even write down algebraic equations describe the way you think, right? Now, why would Boole try to do such a thing, and how did he even expect to succeed, right? Now, it's very important in this that Boole was largely self-taught. Keith Devlin, in fact, says that Boole did this because he didn't have a teacher. If he had had a PhD guide, guide would have said, ye sab chhod do. This is not the sort of thing that will get you, a degree and a postdoc and all that. You do something manageable, right? So Boole was, he was running a bookstore. He was the son of a, shopkeeper, and then he didn't have money, and he didn't go to formal school. He was self-taught. He was very much interested in mathematics. And then he did JEE tuitions, basically. I mean, so he was basically, running math tuitions for children. And after some point, he, somebody said he should run a school. So he was running a school. And then he caught the eye of De Morgan, who got him a professorship in Cork. And it was because of De Morgan that he started looking at logic at all. And in fact, De Morgan was his mentor. So he didn't want to tell him that what De Morgan seemed to be doing looked very silly to Boole, I think, right? But he didn't want to say that, so he decided to just write a book. And that's how he got into this thing, which we call Boolean algebra. And and Boole's essential idea, and this is a very simple idea, right? So you represent by symbols, classes, collections, and you don't care about whether they exist or not. And you can see the foundations for computation in the way you are thinking about it. And this is how modern programming languages you are used to thinking. But you don't worry about these things. And this was very important departure at the time, because Leibniz wanted to talk about an algebra of concepts, but he didn't succeed because he kept on running into all kinds of existence issues. And so as far as Boole was concerned, let the symbol 1 represent the universe, which comprehends every class of objects, whether existing or not. The statement true, it's simply true by default, right? It represents anything that you want. And then, simply write down algebraic equations involving collections, right? So for instance, I mean, he starts with multiplication as the basic operation, right? If X represents Indians and Y represents logicians, XY represents Indian logicians, that's all. And X plus Y would be to, taking a class and dividing it into two parts, male and female, for instance. And he was really interested in exclusive OR, partitions really at the time. But then very quickly he says, even with such assumptions, so you can see that certain equations hold. This is what he called the laws, right? And so in the chapter in Mathematical Analysis of Logic, and he basically says that, since you said 1 is this everything, right? The entire class. So if I want to talk about the complement of X, 1 minus X is a good representation. And that's it, right? Since you have said all X is Y is represented by XY equals X, from that you can actually conclude X times 1 minus Y is 0. And that gives him the empty class. So he goes on like this. And so for him, it's very important that whatever you do, you should be doing equation solving. That's a familiar mathematical thing to do, and that's what you should do, right? And he wanted every equation to be solvable. And so he was very proud of this method, and it became the highlight of this. The second book was basically an effort to correct his first book, some mistakes and so on. And it's a 424-page book. And what is very interesting is that its part one is logic, part two is probability. I think very early on, he already realized that you could also be talking about these collections as events and attach probabilities to them. Okay, so this is, so the connection is fairly interesting and important. I mean, if we want to think about it in terms of sigma algebras and so on, the connection becomes very clear. But Boole was, thinking about these things before such things existed, right? And what is very interesting is that I hope somebody will actually read these things nowadays, because he actually talks about this calculus of probability, as he calls it, and he says it's very important for uncovering fundamental laws governing society because by looking at large quantities of social data. He actually says governments today are collecting a lot of data, writing in 1854, right? And to analyze this data, you need this calculus of probabilities. So he sells both his part one and part two as a way of talking about what machine learning people want to do today, right? And interestingly, part one caught the imagination of people. Part two is largely no, and only now computer scientists are going more into that. And but Boole was not really interested in axiomatic foundations. I mean, he was really interested in doing equation solving. He knew that the three laws that he wrote down were not enough, so he added some more. But he didn't particularly check whether these are complete or not. Is it sufficient? He didn't bother. But as I said, with remarkably little fanfare, he presented a radical new foundation for this algebra of logic. And Shannon used this to actually build up his paper on mathematical theory of communication, and this idea of logic gates and all these things came up later. Now, a very important rule for Boole was this use of 0 and 1. The only idempotent numbers are 0 and 1. And so as far as he was interested, so basically you should use common algebra, but wherever you use only 0 and the values are only 0 and 1, it should translate to this logic. That's how he arrived at Boolean algebra. And so, I mean, this is Boole's algebra, which what we call Boolean algebra is slightly different because we use inclusive OR and not exclusive OR and so on. But basically, this was the idea. And let me skip all these things. It's basically reworking by later mathematicians. I don't want to. So, and Halmos says perhaps one of the most influential mathematicians of all time. Because by reducing reasoning to doing algebra, Boole opened up the possibility of building up a logical machine. And after that, Boole completely lost interest. I mean, he just wrote these books, got back to his integration and differentiation, and wrote more stuff on differential equations. And he died very early. I mean, he died at the age of 52 or something, and very tragic. I mean, he was one person who, riding horses, who used to go to the university every day, and I think it was snowing, very cold, and he caught cold and died of pneumonia. So something of that kind. And and Jevons built this mechanical reasoning machine and actually demonstrated it to the Loyal Society in 1870. And as an implementation of logic, it was a stunning early ancestor of the modern electronic computer. And here is Charles Peirce, another mysterious figure. And this quote I find very interesting because he says, the value of logical machines seems to be in their showing how far reasoning is a mechanical process. Calculating machines are specialized logical machines. And I've highlighted that, so he doesn't. So, and he says precisely how much the business of thinking a machine could be possibly made to perform and what part of it must be left to the living mind is a question not without conceivable practical importance. Typical old English thing. But he's trying to say that basically, sort of thing that we talk about for AI today, right? And artificial agents and reasoning agents. And so he's trying to ask, how much of it actually should be left to the machine, how much a human being should do is something we should decide. And this is of not without conceivable practical importance, according to Peirce. Okay, So let me quickly fast forward to the 20th century. Now, here's a question that I usually ask, and can you ever say when a discipline of study was born, right? And even Boolean algebra, I mentioned Boole's algebra, and as I said, Boolean algebra as we know it is much later. The Boolean algebra that we study today was really Birkhoff, 1917. But yeah. So the thing is, in general, you can't say, but for mathematical logic, we can. And I claim it was September 7, 1930, Sunday at about 3:30 p.m. You can do the Jatakam and all that. And this was in the Königsberg, in the second conference of the epistemology of the exact sciences, kind of thing people used to talk about, and a German city. So this was the last day of the conference, around now, 3:30 p.m. And this is typically the kind of time, last session of a conference, there is a panel discussion. And there is a panel where on Foundations of Mathematics chaired by Hans Hahn. Speakers were Carnap, Heiting, von Neumann, Schultz, and Reidemeister, all famous names in mathematics. And they represented different schools of Foundations of Mathematics. And pretty much, Hahn, as the chairman, was summing up and saying, what you say in every conference, this has been a great conference, we should have more of these things and so on, right? So we should plan for the next conference, right? One of the important agenda for end of any conference is to plan for the next, and sort of thing that he says. And at that point, a young man gets up to make an incoherent speech. I mean, what these people were saying was, look, intuitionism, formalism, logicism, there are various schools, and they are all reconciled nicely. Von Neumann had come up with this very beautiful construction of ordinals at the time. So you could show that numbers could be, not only numbers, but all ordinals could be placed. And basically all the Cantor stuff and all was not a problem. Everything could be set up formally and neatly. So it all looked very good. And as I said, there is this young man who got up and made an incoherent speech saying that it's not obvious that it's all so good that and so on. There are many problems, and the moment you work even with numbers, it becomes difficult, etc., etc. And this was Kurt Gödel. And he had just announced his incompleteness theorem, and nobody had a clue what he meant. But they say you can't keep a good theorem down. Von Neumann was always the quickest of the lot, and he was sufficiently bothered by what he heard. So he caught him at dinner time. And, apparently Gödel was always a loner. He was eating alone, and von Neumann went to him and asked, so what was all that nonsense that you were saying, right? And then Gödel started explaining what he had in mind. And von Neumann later told somebody that he felt a chill, that if this guy is right, either this guy is hopelessly wrong, or if he is right, all the stuff that we had been talking about was wrong. And so he told him to write to him. And then he went off. He sailed. I mean, those days ship, right? He took a ship to go to Princeton. And all the while he was thinking, and being von Neumann, I think he could construct quite a lot of the stuff himself. And so he reached Princeton, and Gödel's, letter, article, whatever you call it, came to him, and he realized that this was his. He was the one who convinced Hans Hahn, who was the chairman of the session, was also thesis advisor of Gödel, to actually talk about it. And those days, that was the idea. PhD student does the work, and the advisor gives the talk in the academy or whatever. So in the Academy of Sciences in Vienna, Hahn talked about this, and then Gödel's paper was published later in September, about a year later. So, and this is all, so basically what Gödel was trying to say was that if there is any system that formalizes arithmetic, then there are always some truths that are going to be outside that you cannot derive. And this was driven principally by David Hilbert's program. And one of the important questions that came up from this after Gödel was, if you take any question on logic, is it satisfiable? Is there a model for it or not? Or is it an inconsistent statement in some sense, right? And is there a procedure for that? Now, Hilbert fully expected a positive answer, which would only need a procedure and not need any definition of effective procedure. Because to say there is a procedure, you just have to give a procedure. And that's what mathematicians were good at. And here is Hilbert. And here is his famous slogan, where he said, "Wir müssen wissen, wir werden wissen." He says, we must know, we will know. He says, I mean, I have the recording of that speech where, it was Deutsche Radio actually broadcast it, and you should listen, where he says there is no such thing as an ignoramus, right? Once you mathematize a problem, you can solve the problem, right? And that's where. And interestingly, it was exactly at the same time, 8 September 1930, and it was in Königsberg. In the same city, there was another function for Hilbert's retirement, and he was a big figure by then. And so they had a big thing. And this is the slogan he said on the same day. That's why I said it's the day when mathematical logic was born, right? And Hilbert's program was something natural. And now connect it with what Boole was talking about earlier, right? And what I talked about earlier is the connection between mathematics and logic, right? Because if your mathematics depends on proof, the main idea is that you axiomatize mathematics like you do in algebra. Hilbert showed how you can do it in geometry, all of these things. So today we talk about algebraic geometry, algebraic topology, algebraic number theory. Algebraization is the paradigm in the 21st century, in the 20th century. And basically for that, you write down axioms, write equations, and you solve. And this was the main paradigm. And you just have to show that all those things that you write down are consistent. And that's a proof that you want. And that proof you do in mathematics as well, right? So as long as you make sure that the consistency proof uses only finite method. Why finite? Let me not get into that. Somebody is interested, I'll go more into it. And his famous slogan was to truth through proof. Truth is a very complicated, controversial notion. Don't go there. You only talk about proof. And proof is all finite statements, right? Finite sequences. And you can always do that, something that mathematicians can do. This was his main idea. Very reasonable idea, actually. And Gödel's thing completely destroyed the Hilbert program. And it showed that if you have any reasonable fragment of arithmetic, there will always be sentences that you can neither prove nor disprove. And if you say that, okay, these are true, so you add them as axioms, then there will be he'll produce a new sentence for you. So it's inherent incompleteness that he was talking about. And then he also showed that, if any system proves its own consistency, then it has to be incomplete. And mathematicians want whatever theory that you develop, you should be able to prove its consistency. That means there will always be something outside it. This is roughly the idea that Gödel showed. And Gödel employed a very simple but powerful technique in this. Basically, he said, every theorem in your system, I can code up as a number. And then he said proofs, after all, are finite sequences, right? They are finite sequences of numbers, which again can be coded as a number. Therefore, a theorem about numbers can be actually talking about it's not having a proof, for instance. That's how he diagonalized. But the main idea is that you are using numbers to code statements as well as sequences of statements. And this was the idea that von Neumann got from there. And he said, this is a brilliant idea, right? So basically what you're saying is data as well as programs that operate on data can all be coded in one uniform fashion. And you can always decode and reconstruct whether you're talking about a statement or a proof, or in this case, instruction or data, etc. This is the famous von Neumann architecture. And here is von Neumann. Yeah. So Gödel's work still left this question open, whether you give any system, any kind of axioms that you've got, and some sentence, does it have a proof or not? And Gödel's theorem does not answer this, because the procedure, if there is a procedure, it could very well say no. There is no proof for both the sentence as well as its negation, right? So neither the sentence nor its negation may be actually provable. Such a sentence will exist according to Gödel, but the procedure may be able to find it. But then after 1931, people did not expect a positive result, but there is a big barrier. How are you ever going to say there is no procedure? If there is a procedure, you demonstrate. How are you going to show that there is no procedure? And this was done by Alan Turing, who showed. So you needed a mathematical notion of a procedure, and that's exactly what Alan Turing showed. And Turing 1936, one of the most remarkable papers ever written. I think it's a paradigm of clarity to read. In a single paper, Alan Turing managed to define the notion of effective procedure mathematically, showed that it can simulate any reasonable notion of computation, and therefore as general as any intuitive computing machine that you might have, showed that it has limitations. There is at least one problem that it cannot solve, namely the problem in logic that we just mentioned. He constructed a universal machine that could take any other machine as input and behave like it. And this is what we use in your compilers and operating systems and so on. So basically, it is in this sense that you can call the computer the mother of all machines, so to speak. And so all this basically says computation arises from logic. But of course, so what? Going back to my original questions. All this says that, okay, it's a decent thing to study. There is some deep connection. So, but what if I don't care for deep connections, right? It's all okay, but why is it relevant today, tomorrow? I mean, I want to do the next revolution in AI. What should I care about all this, right? So one might ask a simpler question: what areas of computing require an understanding of logic, right? And now, one important area, and I know that some people here do a lot of work on these things, but basically to accept that reasoning about programs isn't easy, right? Reasoning about that little puzzle that we saw isn't easy. Reasoning about programs can be quite complicated. And anyone who tries to maintain code written by somebody else knows how painful it is trying to figure out what a program does. I mean, it's not only a matter of documentation, is it? I mean, it's, you can write fancy documentation. It's still very, very hard to figure out what a program is doing, right? So one of the things that started in the 70s was by Edgar Dijkstra and developed by Tony Hoare and David Griess and several others, with the idea that you develop programs along with proofs. And then later people said, okay, maybe code can carry proof too. I mean, today we talk about proof carrying code and so on, right? So there are ways, but most importantly, it is clear that some learning to write some assertions, this is true at this point, this is not true at this point, already helps thinking about program. That much at least is clear. And programs, when you say programs now, what programs are you talking about? Low level, high level, it doesn't matter. And in general, you talk about system behavior. And then when it comes to reasoning about systems, the more complex the system is, it's harder. And therefore, some formal specification is needed and some formal verification is needed. And this is another area where logic comes in, especially the reasoning part. Now, system specification is one of the things where there is a lot of work on this. Basically, how do you specify what a program should do or a system should do? I mean, take a simple example like sorting. Very easy. I mean, I've read it in a number of places, Sorting programs take as input an unordered list and produce as output an ordered list. Is this okay? That's a statement. Of course not, because I can always write 1, 2, 3 as the output, right? I mean, a program that simply writes 1, 2, 3, 4, 5, 6 will give an ordered list. Who cares what it does about the input? You want to say the output is a permutation of the input because it shouldn't have extra junk also. I mean, if it sorts the given list and then adds some garbage also, you wouldn't call it a good program, right? So, I mean, this is the most trivial use of a specification to say. I mean, in general, if you're going to have a contract between the one who's demanding the system and who is supplying the system, I mean, specification is supposed to be the contract. And therefore, formalism is extremely important to, and this is at the most basic level that you're talking about. In general, your requirements are pretty complex. So formal specifications are best written in a logical language is something that has taken quite some time. And now there's a lot of flexibility to all these logical languages and you can figure out a lot, but at least the semantics is very precise and this is the main idea. And then you can talk about verifying whether the system does what it is supposed to do. And this is not a trivial part at all. And so formal specification doesn't necessarily mean that you're able to verify things either. And once you start looking at these things, logic plays a considerable role. Let me leave it at that. But then it gets much worse when you say what you mean by a program, right? Now, when I switch on the computer, what kind of software do we use typically, or your mobile or whatever, right? How many programs do you know which you switch on actually which compute something and give an answer? I don't know. Which solves a particular problem. I mean, that's your idea of an algorithm, right? Which takes some input, does some processing and produces an output. The time we use programs that never terminate and give an answer, right? Operating system, what answer is it supposed to give? Browser, editor, none of these things. They're not, they're basically reactive system. They're just sitting there, get some input and behave in response to the environment, right? And so they're like how physicists study open systems, closed systems, etc. And so is the same way of reasoning about programs that are supposed to read all the input, process, and produce the output. Is that the same way you think about all these things? Is it the correct line of reasoning, or is there some other line of reasoning? Is the set of requirements different? So this is, given salary to several of us for a long time. And these things require reasoning about temporal properties. It's not about just state-dependent information. It's not just truth, but truth in which state, truth now, tomorrow, eventually, etc., etc. And so this gets already the reasoning, the pattern of reasoning. As I said, reasoning about computation in general, reasoning about programs with a particular structure, and then reasoning about potentially non-terminating system behavior adds complexity to the kinds of reasoning that we start doing. So your logic gets more interesting, more challenging, and more rich. And then comes concurrency and interaction. The moment, like, go back to that sum and product puzzle, right? I mean, so when people start interacting and talking and communicating, right? And the more, autonomous concurrent components that interact together in complex ways, it's harder and harder to understand globally what the picture is. And in terms of, you would really like to say, okay, this is what the component does, have all these things and somehow derive the behavior of the complex system. And this gets harder and harder. So the patterns of reasoning that we are talking about, and we are putting out in the world, right, as computer scientists, and this becomes. And one fundamental problem that concurrent systems, distributed systems have is that the bugs are not necessarily repeatable. Right. I mean, and this has caused much angst and dissatisfaction to a lot of people. Like, as long as bugs are repeatable, when you do debugging, right, you keep doing, and again the bug appears, and you feel safe, and you can fix it. And it doesn't appear anymore, you are happy. But in a distributed system, you think you have fixed the bug, and then again it appears, it's a problem, right? And if you can't make sure that the bug keeps coming up, then you don't know whether you've solved the problem or not, right? So why does it happen? Now, that is a question for a logician to answer, right? So what are the patterns of interaction that lead to these? And you can't just, hope to catch some problems. You can catch at runtime and rectify them. Some you cannot. Can you classify these things? Can you classify these properties? Can you say which one, when, where, what? Ask Deepak, he'll give you answers. I think he has worked on enough of all these things. And logic and automated tools today play a major role in this kind of reasoning. So far I was talking about logic as what people do, but the moment tools come in, actually it becomes very, very rich. And this is really what's happening today. Now, particular examples that I would take in reasoning of this kind of security, right? I mean, I've been talking about logical structure in various ways, but what do we really mean by that, right? Now, security is all about locks and keys, right? Now, why do you lock your door? Why do here is my, I think, guest house room key, right? No, I locked it and came. Now, what is the point in locking the door? I mean, it's because I believe that guest house office has a copy. I have this key, maybe 2-3 copies, and this. If it's freely available in every, shop in Bangalore and this thing, it makes no sense for me to lock the door, right? So security, feeling secure is a matter of certain assumptions, right? There are many assumptions that are involved. And in particular, there is some proof of security, right? There is some, so when I buy a house and get a key to it, the key signifies both enabling and right of possession, right? In the sense that I can use the key to get in, and it also shows that I have the right to enter. Now, a thief who steals my key is enabled, but doesn't have right of possession, right? And similarly, when I lose the key, I'm not enabled, but I still have right of possession. I don't have the key, right? Now, a login password is something like that, right? It's the key to which I enter, but does it have the same properties? Now, we tend to anthropomorphize a lot. We behave as if it's like that, but is it the same? Now, in access control theory, you read all this stuff like A may have access right to perform an operation X on an object O, and then A may hand over a key K to B. And then, I've seen assertions like A allows some action alpha to express this. But then you can ask, if alpha implies alpha prime, A allows alpha, does it imply A allows alpha prime? When I give you something, have I granted you to the right to everything that's implied by that? That gets very hairy when you start doing, and it gets much more complicated. Let me not go down this. My point is that security is one place where you can really see the need for formal logic, right? Secrecy, for instance, says what is meant for X should not be seen by Y. Privacy is not the same thing, and there is a lot of mistake that in the beginning people make. I have my notebook on my desk. There's nothing secret in it, right? But still, you have no business looking at my notebook without asking me, right? What I've written at some automata theory notes or some nonsense like that, right? So there's absolutely nothing secret on my table, but you still have no business. That's what privacy is about, right? Secrecy actually means that you shouldn't look at it, right? Because if you look at it, some compromise will happen, something will happen, right? So, and so on, authentication. Let me not go into this. So main point is that if you feel secure when there is a proof of security, right? And so it's basically a logical exercise that is going on that underlies whatever you can call security. Let me take another example. Here is we had Uttar Pradesh elections and all these people showing their voter ID prominently, right? And mechanisms for implementing elections are crucial for modern democracies. And you might say a formal theory is relevant. But what logical properties we expect of a social procedure like this? Right? This is a large distributed algorithm in action, right? And now you might say, okay, what are the kind of properties that you would expect? Eligibility of voters. Only those who are eligible should vote. More or less that's true in India today, but it has taken a very long time. Not very long ago, there were elections where all kinds of Janta would vote. Booth capturing was not a unknown thing. Confidentiality of votes, right? This is something that you expect, right? That the way I voted should not be known to others. But are there more? If you start thinking about it, all kinds of properties start. I'm just saying, bringing a logical lens to these things, you start seeing many things. Like, for instance, universal verifiability, right? We take it for granted that every vote that has been cast has been counted, right? How do you know? What if in one district, 4 booths, the votes were not counted, in another district, 8 booths were not counted? Then the results are not reliable at all, right? So this is what universal verifiability says. An even more dramatic requirement in a democracy can be individual verifiability. I should be able to verify that my vote has been counted, right? Now, is it a right? Partial results. West Bengal election had 8-phase elections, right? If at the end of 3rd phase, you can start getting an idea of how 1st phase went, it will be a terrible problem with the elections. Another very interesting thing is no voter should be able to prove to another how she voted, right? Why would you want this? If not, Deepak can come and say, I'll break your legs if you don't prove that you voted for me. Of course, you could bribe me. That is a more nicer version of it, saying I'll give you 1,000 rupees if you show that you voted for me, right? But much more interesting case, and this is something that so coercion is a problem, right? So these are all properties that you would want. Now my question, can we even prove that these requirements are all consistent? Can we show that there exists an election in which all these properties can be guaranteed? And here is a theorem that says that there is no election procedure that guarantees all these properties together, right? And so something that looks reasonable, unless you logicize and formalize, you're not even sure whether the requirements that you've got are consistent. And on the other hand, there is another theorem which says that if you give up one of the two, universal verifiability or individual verifiability, then there exist election procedures that assure all the rest. There exists is very, very different from realizing it in a way, that a society accepts, etc. But my point is that even mathematically, showing something like this is non-trivial, right? And then it's a democratic decision on your part to say which properties I want and which properties I do not want, right? And this is basically the point. Maybe I should skip ahead more examples. Let me skip these things. Okay, this is a. So Roger Needham's famous statement: security protocols are 3-line programs that people still manage to get wrong. And databases, I think for anybody who knows SQL, basically it's just first-order logic. Databases is one area where algorithms for query evaluation, query optimization, they all involve procedures for analyzing logical structure. And yeah, so let me skip. Artificial intelligence is the major area, knowledge representation, where logic plays a major role in areas like planning, common sense reasoning, robot interaction, swarm robots, many areas, inductive learning in particular, not ML. This is the and current holy grail, explainable AI, and something of a big deal, where logic can play a major role. Okay, so logic has traditionally provided foundations for mathematics. Now you have new foundations coming for programming languages, complexity theory, concurrency theory, game theory, and so on. And as I said, complexity theory again, the notion of NP completeness really came from the study of Boolean satisfiability. So the need for foundations is acute, especially computing is greatly technology driven, and we tend to miss these things, and that's why foundations are important. Mathematical logic has become a research discipline of its own by now. Interestingly, the interaction between logic and mathematics has not been that strong in the last century, but this is to be contrasted with the tremendous richness of interaction between computing and logic. And it has led to philosophical logic as well. So the last question that I want to raise, and is computation logical in nature? Is there this is how computation has developed. Computing machines all the way to our laptops have come. Is there a notion of physical computation that might be different with different properties? We really don't know. And this is a very important question. Is logic hardware independent? We believe so. Can you prove so? I mean, does it take a particular kind of brain to do logic, right? And there are very nice experiments on birds, on primates, doing different kinds of patterns of reasoning. And so we would like to know what Boolean logic is really about. Does it require a particular kind of hardware that has come in evolution? Or we don't really know good answers to any of these. And also, the notion of computation we shouldn't take for granted, the way that was developed. I mean, for instance, what does the internet compute? It's a good question to ask. I mean, these are fairly deep questions to ask. And I think, the answers finally lie in logic. That is why I'm saying that if you want. So why should we study logic? Well, logic is unlikely to help anyone come up with cleverer algorithms. On the other hand, it is indispensable for developing error-free systems. Formalization helps in disciplining thought, in communicating ideas, and in being rigorous. So I would say the ultimate answer to the question is it helps in being rigorous. And logic is really for those who need answers to why questions, right? I don't want to just say that this works. I want to answer why it works, right? So why does this work? And why not that, right? I mean, both questions are very important. And why does this work? Why doesn't that work? And, okay, so thank you very much. Oh, I think here. Okay, I'll come.
All logic are equivalent to the Boolean or the true false. Are all kinds of possible logic equivalent to the Boolean?
Yeah, Boolean.
Or Boolean or just that true false?
Yeah, okay. So I mean, as I said, if you want the axioms of Boolean algebra, then study multiplication, how it distributes over addition, all these things, then there is a theorem which says that this is basically two-element algebra is isomorphic. So there is a mathematical answer. But then you might ask, instead of 0 and 1, suppose I use the continuum. Every x can take value not 0 or 1, but any real number in the interval 0. Then you can give a probabilistic interpretation to it. I mean, you think of x being true as probability 0.6 and y 0.4. And then you actually think of these as operations with probabilities. For events, you can talk about intersection. And this is how we learn in school. So there are consistent interpretations of Boolean algebra with the two-element, multi-element, 0, half, 1. But it won't be exactly Boolean logic. They'll have to give up some things. And so you can have three-valued logic, multi-valued logic, continuum logic, fuzzy logic. There are any number of variants that you can think of. Invariably, you will have to give up some axiom logic. So instead of Boolean algebra, you make it a quasi-Boolean algebra. Some other derivative. So there's a book by Rashowa and Secrecy called Mathematics of Meta-Mathematics, which actually looks at all possible ways in which you can modify these things and for each of them gives some logic. So not equivalent, but related. That is the chart. Yeah.
It's just maybe a possible extension to the applications that you mentioned. This was not. So I want to know your thoughts on it. So there is a recent area that's coming up. It's called neurosymbolic AI, right? So
I've heard of it.
People have, from symbolic AI to statistical AI, and now people are talking about, why not merge both of them, right? Which is kind of giving interesting results. I wanted to know your thoughts on that as an application.
I don't know enough to be able to say, enough to be able to answer that. See, the point is that logic, as I said, with the probability interpretation, right? You can do a lot. And this is, in fact, my answer to the previous. When it comes to statistics, what you might call logic in the large, right? One of the foundational questions that have remained is whether logic in the small is the same as logic in the large, right? I mean, one of the areas that I work in is what we call large games. Games, rather than think of cute little games played by 3 people and 4 people, you think of, games with 40,000 players, infinitely many players, right? Now, are they the same principles that govern game theory, right? In general, I would say the foundations on that are shaky. We don't have as clear an answer, right? Why I'm saying is that statistical inference, right? When you try to give logical foundations, right? What you're trying to say is that if large number of people go for P and a large number of people go for Q, you would like to believe that a large number of people go for P and Q. Sorry, you try to do such things, you get into trouble, right? So historically, people have been trying this for a long time. So this is one of the, my suspicion is that if you want to combine these two techniques, there are some important foundational questions to be, addressed. The good thing is that, like in game theory, to take an analogy, in 2-player, 3-player games, like board games, right? You really have to worry about if I do this, he will respond with this. And if he responds with this, I can do with this. But he knows that I would respond with this, therefore. This is what, game theorists would call intersubjectivity. Equilibrium is about all that. Now, when you go to 20,000 players, all this disappears. There are like very nice mathematical structure and strategy spaces you can make use of. Good probabilistic reasoning will carry you through. So small and large are also different in certain ways. And central limit theorem is one of the beautiful things that tells you that after a certain this thing, you might as well think of it as infinity. Nothing goes wrong, right? In the small, it doesn't quite work. So how does logic exactly work in the small and the large has always been a, good foundational question. Doesn't mean that it can't be answered. Maybe this is the time to answer these things. And so But my suspicion is that when you try to combine these things, certain foundational questions have to be, you have to find some, or you do like physicists do, different energy scales, you apply different techniques, right? So maybe, in the small, you use certain logical techniques, in the large, you use some techniques with some good transitions, I don't know. But yeah, I mean, yes. Yeah.
Symbolic techniques really work very well for small cases, right?
True.
They scale up to a point. Right?
Up to a point. That's the point. And what is that? We don't know.
Yeah.
Yeah.
But we have character guarantee. We can have.
Okay. Yeah. No, I know. That's why I'm saying it's important to do research in that. I'm just saying there are no textbook answers as yet. Yeah. I mean, there is some research to be done, is the point. I'm not saying it's impossible or any such thing. I'm just saying there are some important foundational issues, and maybe those are likely to be answered.
Context of the document, usually we hear people saying illogical or not logical. What is it that you can now say is not logical? So far as
yeah. So the thing is that people are often irrational in some ways, right? I mean, that's clear that human beings tend to be not always rational. And there is a very nice, book called Predictably Irrational. What is very interesting is that human beings are not only irrational, they're irrational in highly predictable ways. Some things that we seem very, rational about, and some things that, so one thing is that you get confused, right? I mean, you get confused after a point, and, you therefore make certain things. So is irrational the same as being illogical? Well, logicians would like to believe that logic is the basis for rationality. So coherence and inability to put things together. As a father, I act in a particular way. As a professor, I act in a particular way. And these are compartments. And in my pattern of reasoning, right, I'm the same person. It's not schizophrenic, but I'm actually inconsistent in many ways, right? I mean, we all do that, right? You go to an ATM, people actually stand in queue. But Silk Board, every vehicle wants to go past, right? And it's a huge mess, right? So if everybody were to behave equally in the same way, it would be easy to do. But, and systems depend on that. So people are illogical in this sense that you use different patterns of reasoning in different contexts. And everybody sees that these are different contexts, so you get on. But at heart, there is inconsistency.
So thank you, Jam, for that very entertaining talk, and also to kind of convince us that we need new logic, which I think I should program and learn more logic. So it's there. It's just give Jam.
And it's an advertisement for Deepak's course also.
Because Professor Govind, small